Welcome to Characterizing Network Traffic. I'm Mike Bird,
And I'm Declan.
and we are Team Bombur.
Bombur. Here are some main points we'll be talking about. The first point is traffic flow and its sources. The second point is traffic load and its behavior. The third point is quality of service requirements. And the fourth point is our hands-on lab, which will be coming soon.
To start off, let's talk about characterizing traffic flow. First, we have to identify our sources and destinations of network traffic. Then, we must analyze the direction of the data and observe whether there is symmetry between the source and destination. Based on that data, traffic flow can be identified as bidirectional and symmetric, bidirectional and asymmetric, or unidirectional and asymmetric. Traffic flow has major sources and stores. First, you must identify its user community, which is a group that uses a particular application or set of applications. This can be a department or a group like students at a college. Next, there are major data stores that must be identified. These are areas in the network where application layer data resides. They're often bidirectional and asymmetric, where the client sends small queries and the server sends large streams back. Think of servers, storage area networks, mainframes, and file hosts. Next, let's look at some types of traffic flow. There's a terminal and a host, which is usually asymmetric. The terminal sends single characters, and the host responds with a larger amount. Think telnet. There's the client and server, which is the most widely used and known type. This is usually bidirectional and asymmetric. Clients are PCs, the workstation, or mobile phones rely on servers that control network resources, such as files or printers. There's also peer-to-peer, which is usually bidirectional and symmetric. Every user is both a distributor and a consumer in a peer-to-peer traffic flow type. Continuing with traffic flow types, there's the server-to-server, which is usually bidirectional and symmetric, but it does vary based on the app. These are transmissions between servers. This one's pretty interesting, and it's known as distributed computing. The flow varies and can require a network simulator to model. A dedicated task manager and multiple computing nodes work together to complete a task. Finally is voice over IP, or VoIP, which has two separate flows: transmission of audio as one flow, and the call setup and teardown as a second.
Next, we'll be talking about characterizing traffic load and behavior. First, theoretical traffic load, also known as offer load, is the sum of all data that all network nodes have ready to send at a particular time. Next, estimate traffic load. To refine an estimate of your application bandwidth requirements, you will need to research the size of the objects sent by an application. Broadcast and multicast behavior is another aspect. A broadcast frame is defined as a frame that goes to all network stations on a LAN. The address of a broadcast frame at that data link layer is 6 sets of 2Fs. A router cannot forward any broadcasts or multicasts. A multicast frame is defined as a frame that goes to a subnet of stations. Layer 2 internetworking devices forward all frames. A router does not forward any frames, multicast or broadcast. To continue broadcast and multicast behavior, we'll be talking about windowing and flow control. Flow control tells the sender how much data should be sent to the receiver. And windowing is when a receiving device tells the sending device that the buffer where the messages are entering is full. Another aspect is error recovery mechanisms. Error recovery mechanisms are a main feature of TCP. It was designed to help node and line failures on the TCP application. Poorly designed mechanisms can waste a lot of bandwidth.
Next, let's talk about characterizing the quality of service requirements, also known as QoS. QoS varies based on the application. Some applications, such as video calls and voice calls, are unable to function if certain levels of bandwidth are not available. The ATM forum has defined 6 bit rate service categories: constant bit rate, real-time variable bit rate, non-real-time variable bit rate, unspecified bit rate, available bit rate, and guaranteed frame rate.
QoS bitrate service categories. Constant bitrate, CBR. Constant bitrate is known as network resources that are reserved in advance and guaranteed for the duration of the session. CBR works to support real-time applications such as video and voice calls. Real-time variable bitrate, also known as RT-VBR, is distinguished by peak cell rate, PCR, maximum burst size, MBS, and their constant bitrate, CBR. Sources transmit in a bursty manner and vary with time. Non-real-time variable bitrate, or NRT-VBR, is similar to RT-VBR, except used for non-real-time applications. Distinguished peak cell rate, PCR, maximum burst size, MBS, and constant bitrate are all NRT-VBRs.
To continue with bitrate service categories, we have unspecified bitrate, UBR, which is intended for non-real-time applications. Think email and file transfers. Available bitrate, ABR, specifies a maximum required bandwidth as the peak cell rate and a minimum usable bandwidth as minimum cell rate. This is not intended to support real-time applications. Finally, there's guaranteed frame rate, GFR. This is designed for applications that need a minimum rate guarantee, but also dynamically adjusting their bandwidth needs. And finally, we have our Characterizing Network Hands-on Lab, which we are excited to present to you coming soon. We thank you for joining. Bye.
Bye.
Hello, everyone. Welcome to a preview of our Characterizing Network Traffic Lab. Our lab will use Cisco Packet Tracer, and where we will develop small networks and simulate some network traffic. As you can see here, a PC0 is currently contacting the server, and you can see some of the network traffic. So that is a brief introduction to what we will be doing in our lab.